Hello guys, it's JohnnyTime and welcome to another smart contract hacking tutorial. Today we are going to solve together the first challenge in a Damn Vulnerable DeFi CTF version 3, the new version with the new soulmate contracts, with the new standards, the flashLoan standard, and today we'll solve the unstoppable challenge. Now, if you didn't watch my previous video about Damn Vulnerable DeFi version 3, why you should solve it and how to get started with repositories and tasks and everything, check out in the description below. I will share the link, and without further ado, let's start with the solution. So here is the first challenge in Damn Vulnerable DeFi, Unstoppable 1. There is a tokenized vault with 1 million DVT tokens deposited. It's offering flash loans for free until the grace period ends. To pass the challenge, make the vault stop offering flash loans, and you start with 10 DVT tokens in balance. So we need to call some kind of denial of service attack to a vault that offers flash loans, so no one else will be able to receive the flash loans. And by the way, if you want to learn more about denial of service attacks or other kinds of fundamentals for smart contract hacking, check out the smart contract hacking course, where we have a lot of subjects, including exercises. So you learn a subject and then you have hands-on exercise similar to Damn Vulnerable DeFi, but just more guided. So I already cloned the repository for Damn Vulnerable DeFi, and I'm heading over to the contracts folder. Under contracts, we have Unstoppable, and here you can see two contracts, Receiver Unstoppable and Unstoppable Vault. Okay, these are the contracts that we have to work with, and under the tests folder, we also have the JavaScript file unstoppable.challenge.javascript. So this is the test file that creates all the scenario for the exercises. For this particular exercises, creates all the states and transactions, account, and etc. Here we have to execute our JavaScript code for the exploitation. So we exploit, we send our malicious transactions, deploy a malicious contract, and here is the after test that makes sure that the state that needs to happen is actually happening. So in that case, we needed the receiver contract. When it tries to execute flash loan, his transaction will be reverted, or in other words, no one will be able to get flash loans from this vault. And if you are not sure how Damn Vulnerable DeFi works, like how the contracts works together with a test file, and it's basically a hardened project, how to run the project and test if you are able to complete the exercise, check out the previous video how to get started with Damn Vulnerable DeFi. So let's start examining the simple contract, which is the receiver unstoppable.sol. This is a contract that basically simulates a user that is trying to get a flash loan from the vault. As you can see, we have some imports over here. We import the IRC3156 flash borrower interface. So we are going to implement the functions in this interface. This is the callback function that will be triggered once we receive a flash loan. We also import the owned contract with soulmate. As we know, we are now using this new standard and soulmate contracts instead of Open Zeppelin, because Tincho upgraded with version 3 and upgraded the exercises from top to bottom. Now we use all these cool new ERCs and soulmate contracts instead of Open Zeppelin. And here we import the Unstoppable Vault, which is the other contract that is responsible for the vault and for the flash loans. So we don't have too much stuff going on here. We have the constructor where we set the pool that offer the flash loans, and this is the basically two functions. On flash loan is the function that is defined in the flash borrower interface, and we are simply implementing it, right? So it's a function that's supposed to receive initiator, token, amount, feed, and data, and it returns 32 bytes. So here we are simply just making sure that the initiator is this smart contract, the receiver contract. The message sender, the one who called this function, is the address of the pool contract. The contract is the right pool asset, and the feed fee is 0. If not, we raise this error. Now, after we did all these checks, we are going to approve the pool to spend this amount of tokens so they can take back the token, and basically we are just returning the money back. We're not doing anything too fancy here with the flashLoan. We're just giving it right back to the pool. And this is another function that we, the owners of this receiver contract, will trigger outside of the blockchain, and it's execute flashLoan. We send the amount, and it's simply just gonna call the flashLoan function in the pool smart contract to request a flashLoan from the pool. And now it's time to deep dive into the unstoppable vault that we are supposed to make stoppable. This is the vault that offers flashLoan that we're supposed to attack. Here we can see all the imports. We have Mathleap by Soulmate, Reentry Guard by Soulmate. We have the ERC 4626, which is the standard for tokenized vault. You can read more about this EIP. I will put link in the description below. And we import everything, all the standards from Soulmate, again, not from OpenZeppelin, the owned contract, and the IRC 3156 interface for flashLoan borrower and lenders. So it basically shows us how to implement the functionalities of either borrower or lender. We already saw the borrower. Let's take a look at the lender. So the lender needs to implement, not like it's recommended to implement these three functions: max flashLoan, flashLoan fee, and flashLoan, which is the function that offers flashLoan that we saw before the receiver is trying to trigger. So let's go and see what's going on in this contract. First of all, we see that we use these two libraries, SafeTransferLib and FixPointMathLib for ERC20 and UN256. We can also see that there is some kind of fee factor, 0.05 Ether, even though it was mentioned in the instructions that there are no fees for flash loans, but there is also some kind of grace period. And this grace period is 30 days. So after 30 days, this is probably going to be the fee that this pool is going to get. And this is the end, the current time step upon deployment of this contract plus the grace period. This is the fee recipient, the account that is going to receive those fees. Here we're defining some errors and events, and this is the constructor. As you can see, we are constructing basically the ERC 4626 vault, which is also a token, ERC20 token itself, with extra functionality. And we are sending here to the constructor the token, the owner, and the fee recipient. And we set here all the parameters. We initiate the ERC 4626 tokenized vault. We basically set the owner by calling the owned initializer. And we set the fee recipient and emit an event. Very simple, very straightforward. Now, these are the two functions that need to be implemented according to the interface. The max flash loan is the maximum amount of flash loans that we are allowed to take from this vault. And we have a check here that the token that we are requesting to take the flash loan is the asset of the vault. If not, we just return 0. So we are not allowing to take flash loans of any token that is not the asset of the vault. And we return just the total asset, which means the total liquidity that the vault holds at the time of calling the transaction. Now, the flash fee, this is very interesting. We can see that if, again, the token that we are trying to request, if it's not the asset, we are just going to revert with unsupported currency. So these checks basically check if the grace period is over, right? Because we check if the block timestamp is lower than the end time, which is the time of the deployment of the contract plus the grace period, then we return 0 fee. But else, if it's not the case, then we multiply the amount that we want to borrow by the fee factor, which is like 0.05 Ether. So this is like the calculation of the fee, but now we don't have it, we're just deploying the contract, so we are inside the grace period, so we have 0 fees, so we don't care. Here is a function that only the owner can call to set the fee recipient. Here is another function that returns the total assets of the vault with some kind of assembly gas optimization. This is Yule code of gas optimization, another new thing that Pincho introduced in the Damn Vulnerable DeFi challenge, but it's gonna simply send the balance of this contract. So this is the total assets. And this is actually the interesting function. This is the function that we need to attack, right? Because we do need to make a denial of service attack and prevent all the other users from requesting flash loans. So how are we gonna do that? Let's go line by line to this function and try to analyze it and add some audit or comments so we can understand it better and see how we can potentially attack it. So this is an external function that anyone can call, and it's gonna return a Boolean. It receives the receiver. The receiver is supposed to implement this flash loan borrower interface, which is one example would be this smart contract. And this is the receiver that's going to receive the flash loan. The token over here, it's the token that we want to borrow for the flash loan, the amount, and any additional data that we're probably going to pass to the callback. Because once we send the money to the borrower, then we're going to make the callback to the borrower together with this data, so he can do whatever he wants with the money and then pay it back to the pool. And eventually we'll have to validate that the money came back to the pool. Here we have some if statements together with reverts, opcodes, basically some validations. So we can already add some audit comments, audit info, validation for amount. So we can see here that we have validation for amount, right? And we can also see that there is validation for the token, so amount and token. Here we make these two validations for amount and token. The user cannot supply amount that is 0. It needs to be greater than 0. And the token is supposed to be only the asset that is supported by this vault. So we can access this asset parameter, which is by default available in the ERC 4626 contract. So if you go here, this is the asset. You can see we are inheriting from this contract. So this is the asset of the vault. So again, user cannot call this function with wrong amount and wrong token. Here we have some interesting accounting check. We are calling the total asset function, and we set the value into balance before, and then we call another function, convert to shares, which is probably another ERC 4626 built-in function with the total supply. And we are making sure that this kind of balance before is equal this result of this function, or we revert the transaction. So here we have another accounting check. So we're gonna add a audit info. We have here accounting check. We will go back to this accounting check later. We need to understand like why they're doing this and how it actually does work. Here we calculate the flash loan fee by calling the flash fee function that we examined before. We send the token and the amount to get a fee. It's probably going to be 0 because we are still in the grace period. Here we are simply safe transferring the token to the receiver. Okay, so we're using the safe transfer lib by Soulmate to transfer safely the token while checking the return value of the transfer function if there is a return value. And we are transferring to this kind of receiver that we received over here this amount of token that he requested. Here we can add another comment, okay, audit info, calculate fee and transfer tokens, right? So these are these two lines of code. So we are breaking down the functions so we can add our comments. So it will make sense very much and it will be very easy to understand. Now here we are calling the callback, basically the receiver.on flash loan. So we are going to call this receiver unstoppable, the callback, and we are passing all the parameters, the message sender, the one who initiated the flash loan, basically, the asset that was requested for the flash loan, the token that the receiver want to receive, the amount, the fee, and the additional data that was passed over here, these bytes, the call data bytes. And we are making sure that it returns this kind of kekak, this hash of flash loan borrower interface. And this is the standardization of receiving and lending flash loans. So it's cool. This is the IRC 3156, but it's not going to help us much while attacking the contract, just to understand how these ERC new standards work for flash loans. So we can see here that he returns this kekak. So we are actually validating that this receiving callback, this on flash loan function, is implementing the interface. This is how we validate it. So let's add some comments here. So audit info, execute receiver callback, right? And validate validate interface/hash. We are validated that he actually supports the right flashloan receiver borrower interface. Now we are here. Basically, what we are going to do after the flashloan was completed, after the callback was completed, we are trying to call the safe transfer from of the token. So we're trying to take the assets back from the receiver. This is how this interface and standard works. So after he finishes the flashloan, he needs to approve, like he did over here, our contract to spend the tokens. So the vault that offered the flashloan can take the tokens back plus the fee, right? So we are trying to take back the tokens, and then we are transferring the fee to the fee recipients. Initially, it's going to be 0, but after the grace period is over, then there will be some kind of fee. And eventually we return true, we're returning Boolean, so there is no case where this function is going to return false. And now that we understand how the flashloan works and how the receiver works, we need to try activate our attacker mindset and our creativity. We need to make sure that this function will never work no matter what kind of user is trying to execute it. So we need to create some kind of denial of service. We need to make sure that every time someone sends transaction to flashloan, it will be reverted. So we need to see what kind of parameters or what kind of state changes we can make. So every time this flashloan function will not work. Now let's see, we have pretty much a lot of revert statements. If we can make sure that one of the revert statements happens anytime, no matter what, we will make sure that this transaction will always revert and no one will be able to call it. So the first, these two checks with the reverts are dependent on the amount and the token. These are arbitrary parameters that are supplied by the user when he calls the contract and the function. And this is something that is out of our control. We don't know what amount on token the user is going to send, so we cannot attack this through these parameters, because these are parameters that we cannot control ultimately and make sure that the transaction will be reverted. So this is not what we're gonna do. All right, guys, if you feel that this exercise is a bit overwhelming or like you lack the basics, the foundation, the grounds for smart contract hacking, we've got something awesome for you. We have the smart contract hacking course that is going to take you from complete beginner to intermediate smart contract hacker. We're gonna cover so many subjects like denial of service attacks, flash loans, DAO attacks, Oracle manipulation attacks, and much more, together with hands-on exercises and walkthrough videos by top professionals, including myself. And also you get an access to an amazing exclusive Discord community to learn with other people as well. And by completion of the course, you also get a certificate that might help you land your first smart contract security researcher job. So check out the link in the description below for limited time discount. We are going back to the accounting check, and we need to find probably a way to make this revert invalid balance always happen. So maybe we have a way to do that, but first we need to understand what is this if statement gonna do. So first we have the balance before, and the balance before is being derived by the result of the total asset function. And the total asset is simply just gonna give us the balance of the token of this Vault smart contract, or in simple terms, how many tokens this Vault holds when we call this function. Now here we equal this balance before to the result of the function convert to shares. So we can also enter the convert to shares function, and we're sending here the total supply. The total supply and the convert to shares are functions that we need to understand how ERC20 and ERC4626 interfaces works in order to understand what they mean. So we can see here that the total supply here is inherited from the ERC20 token. We can also enter it and jump directly. Let's open here ERC20, and we can see here that it's a state parameter of total supply, and it's simply just gonna count here the total supply of the token, the ERC token that we're requesting the flash loan. And we pass this total supply to this convert to share function, which we can see over here that is implemented inside the ERC 4626 Sol contract that we are implementing. So let's jump into this contract, ERC 4626. In order to understand what convert to share function, we need to understand what are tokenized vaults. Tokenized vaults are basically vaults where you can deposit multiple tokens and then people can purchase a share of this vault. You can look at it like an index fund in the stock market. So we have the S&P 500, which is an index that holds the 500 biggest companies in the New York Stock Exchange. So you can create any vaults that you want. You can deposit tokens to them, and then people can purchase shares of this vault. And these shares are representing the whole assets of the vault. Now, this is the function that converts shares to vaults. Convert to shares, we have convert to assets. So we are calling the convert to shares function, and we are sending the assets, the amount, and want to receive the shares of the vault. And we need to understand how it works. So let's see. First, we set here the supply. The supply is the total supply. We check if the supply equals 0. In our case, it doesn't equal 0 because we already minted some tokens to the vault and to the user 10 tokens, right? So this if statement is not going to work. So we are not just going to return the assets, but we're going to return this statement instead. So it's going to be asset dot mul div down supply and total assets. So it looks fancy and scary, but it's not that scary because this line of code is simply going to do something like this. So I'm going to do here audit info. It's going to return basically assets multiplied by supply divided by total assets. Okay. So this is what it's going to do, but with some kind of overflow protection because we're using mul div down function by Soulmate safe math library. But this is simply, it just looks scary, but it's just going to return this with some kind of safety checks. So assets multiplied by supply divided by total assets. Now, if we can somehow manipulate either the assets or the supply or the total assets, so this result won't be equal just the amount of tokens that this smart contract possess, then we will make sure that this if statement will be true because this result won't be equal the balance before, and this will be reverted with invalid balance. Now, how do we do that? How can we make this kind of imbalance in the accounting? Now, I want you to stop, activate your creativity, your attacker mindset, and try to think how you could do that. So let's try to assume and see what this convert to share function returns. So we are going to send here the assets. The asset that we're going to send here is the total supply. And we already know that total supply is 1,010,000 tokens, right? So it's 1,000,000 tokens on the vault and then 10 tokens on the attacker account, right? This will be multiplied by what? By this kind of supply, okay? The supply of this vault is only 1,000,000 tokens because we have only 1,000,000 tokens on the vault divided by total assets, which is again 1,010,000 tokens, right? So we are simply gonna, this multiplied by this divided by this are just gonna be returned 1,000,000 tokens, right? So 1,000,000 tokens is going to be returned, and 1,000,000 tokens basically equals the balance before, which is 1,000,000. That's why this if statement is going to be false, and we're not going to revert in transaction. Now, how can we make this convert to share function return a number that is different than the balance of the vault? Now, these assets represent the total supply, and it's going to stay the same. It's going to be basically 1,010,000 tokens, and the total assets is going to be the same also because this is okay. This is the same, the total supply. So it's going to be 1,010,000 tokens, but this time the supply is being changed. The share supply is being changed to 99.99 because we basically inflated the token balance of the vault and basically deflated the value of the shares. So basically we created some kind of accounting issue simply because we just sending tokens directly to the vault without going through this kind of deposit function. We are not depositing assets to the vault in order to mint those shares. We're just sending tokens directly, and that's how we can make this mismatch between this total asset function to the convert to shares function. So this if statement will be true, and this will be reverted no matter which user is actually calling this function. So now that we understand how it works, let's try to exploit it and actually run the attack. So we need to send tokens directly from our attacker account to the vault. Here we can see the constants, we can see all the accounts and the contracts that are going to take place in this exercise. Here we deploy the token and the vault itself. We expect that the asset of the vault is the token. Actually, here we approve some tokens and send them from the deployer to the vault. We do some kind of balance checks, and our attacker account is actually the player account. So we need to send tokens from our player account to the vault. So I'm going to call the token smart contract, and I will do await token dot connect player. So I'm basically going to send transaction from the player account, because we are the player account that holds only 10 tokens, to the token smart contract. And I will call the transfer function, and I need to supply two parameters for the transfer function. The first parameter is the receiver, and the receiver is the address of the vault smart contract. So I'm going to do vault.address. And the second parameter is the amount. Now I can send only one token to break the accounting, but I also possess 10 tokens. I can send all the 10 tokens. I can send just one we, doesn't matter. I just need to send fraction of amount of token directly to the contract in order to break the counting. I can send all my balance or just one we of token, the smaller amount of units in order to break the functionality. So this is supposed to break the functionality, break the accounting, and prevent from the user later to request the flash loan. And let's see if it actually works by running the test. So in order to test if our exploitation work, I will do yarn run unstoppable. And let's see what happens over here. And it worked. We were able to pass all the tests, and the challenge was succeeded. Congratulations, guys. You submitted and completed the first Damn Vulnerable DeFi challenge. Now, if you enjoyed this video, subscribe to the channel and like the video for more awesome CTF solution and awesome smart contract hacking content. Thank you so much, and I will see you in the next tutorial. Bye-bye.